by the way? You can, good. So should I just go ahead, or does anyone need to introduce me?
Go right ahead. Kevin is otherwise occupied.
All right, okay, no problem. Okay, good. So let me, I'll share my presentation then. And I like doing some like live demonstrations and code reviews and all of that. So you can look forward to that as well. And I gave my talk an interesting title: Can Forth Liberate Programming from the von Neumann Style? Those who know the paper by John Backus might recognize the wording, where he or at least popularized the approach of functional programming sometime after he experimented with other programming styles after he came up with Fortran. Now, the key lessons are to explore the principles of array and functional programming and demonstrating how to create a language in Forth. And this is something that I'm trying to demonstrate to people and teach some students. Forth isn't just a language, it's a language that you can use to create other languages. And for the demonstration, I will show how to generate this Chinese multiplication table, which is a challenge that I've given some people to do this month. It's just like a multiplication table: 1 times 1, 1 times 2, 2 times 2, and so on. But it has a particular shape and layout, and I found it a good example to illustrate the principles. So a little bit about John Backus, for those who don't know. This is the guy behind Fortran. He also invented the Backus normal form, or at least formalized it, for describing syntax of programs. So we as Forth programmers like to avoid syntax, but you have to admit it is a useful tool. And yes, again, it's in the name, BNF Backus normal form. Now, the part that people don't know much about is that it actually helped to popularize functional programming, because in 1977, he was awarded the Turing Award. And as part of this, you get the chance to give a lecture. So he gave one on this topic, well, with this title right here: Can programming be liberated from the von Neumann style, a functional style in its algebra of programs? And people must have been thinking, what's this guy going to present? Well, in this talk, he makes some statements that I think it seems like it was quite ahead for the time. I'm not going to read all of this here. I might just point into the paper, but let me just read the first few words here. Conventional programming languages are growing ever more enormous, but not stronger. Inherent defects at the most basic level cause them to be both fat and weak. Their primitive word at a time style of programming, inherited from the common ancestor, the von Neumann computer, their close coupling to semantics, to state transitions, their division of programming into a world of expressions and a world of statements, the inability to effectively use powerful combining forms for building new programs from existing ones, and a lack of useful mathematical properties for reasoning about programs. So like a huge list of things. And I think many of us Forth programmers, we might not agree with the conclusion, but we recognize these features even in languages that are used today. So you gave a comparison, and you're calculating the inner product. So this is how it would look in Algol or any kind of C-like language. And what you're doing is you're iterating through each element of the vector and multiplying them and then assigning them. And he was saying, well, why are we thinking about problems like this? Also, this for statement isn't something that the programmer can take and reuse and generalize in all kinds of places. For example, this n value here, that n value is fixed somewhere above in the program. So if they want to work on vectors of different sizes, the programmer then has to go and change that bit. So why do they have to do that? It's not related to this structure here. You didn't like that kind of close coupling. On the other hand, on this right side here, you've got a functional version. And instead, what you have are functions like transpose, multiply, plus, and you have these things called combining forms that put together the functions to make a program. So his thinking was something like, when we design a program, we should not be thinking so much about objects and data, but programs. You make a program from programs. And what you do to achieve that is use combining forms, but that's easiest to do when you adhere to the principles of functional programming. So this is just in a nutshell kind of thing. If you want to read up further on it, I will supply a link to the paper. But as I say, the main thing I want to illustrate is how I use Forth to explore some ideas in this paper. So this is what the original looked like, and this is how it looks like when I do it in Forth. All I had to do was define the words that were used in the paper. For example, transpose, I define. I had to define something that was equivalent to the multiply that was used, which I call times 2, which, don't get confused, it doesn't mean multiply by 2, it means multiply 2 numbers in a vector, and so on. So very, very easy, actually. For simple examples, all I needed really was bump allocation. I've not implemented a garbage collection or reference counting thing because it's not necessary just to examine a few one-liners in a paper. So now we start looking at the code, and we can either look at this, or I do have the original code itself here. So let's have a quick look at these first few lines. So about up to line 12 is where we define the main engine. We have this constant here, which is how much memory you allocate. And then you've got a number of registers. A register for pointing to free memory, register to store the length of vectors during operations, a register to hold a function, because sometimes when you're executing another function, you need to keep a function stored in a register and keep referring back to it. It just simplifies a lot of code. This one is just for figuring out how big a vector is. We'll come back to that. And then one of my favorite registers is this one that points to a vector. So this register I use a lot because when you're working on a vector, it's actually easier to not always keep it on a stack, but store it in this register and operate on it from there. So here we have the definition for the free memory pool. And if you want to reclaim your memory, you just use the word reset, which just deallocates everything. Again, this is for very simple examples. It's not intended to be a full system. Then I defined the word new, which gives you one free cell of memory. It also checks whether you've run out of memory, just in case you get caught out. Using the word new, I implemented vec, which stands for vector. And the usage is basically you put the elements on the stack, and then you put the number of elements on top, and then use the word vec. And what it will do is it will go down that stack and put each element inside of a vector in memory. I don't particularly like deep stack, but you know, if I've seen Bill do it, and if Bill can do it, then I can do it. So this is just an accessor word the length of the vector is stored in the first cell. So if you get a vector as an address and you use you fetch the first element, is the length. The rest of it is the contents. That simplifies a lot of code. And then one of my favorite parts here was this word, which was inspired by something I saw in some work from Charles Moore, which is the idea of fetching and incrementing register at the same time. So I use this pvec at plus, and it does simplify a lot of code because you're essentially you're fetching a value and you're also incrementing the register. So in many loops, that's all you want to do, but with stack juggling, that gets complicated. And the rest of this is just definitions that help me. I added this word here and this word to help me to have a friendly syntax for vectors. So you can, this is how you write a vector using my language I've made up here. And yeah, just the rest is printing words, and functions that you can use to build programs. So which program did I have a go at implementing? How much time do I have left, by the way? I know I was late coming on, but.
Speak until you're done speaking. How much longer do you think you have?
How much? It depends on what speed I want to go through it, but let's see.
You wrap it up in 15 minutes.
Oh, easy. Yeah, I can do it easily. Sure. Okay. And within 15 minutes.
Take a breath. Don't worry about it.
Okay. So I've loaded the program in here, and this right here is the Chinese multiplication table that I've calculated. So the way to interpret this chart is 1 times 1 is 1, 1 times 2 is 2, 2 times 2 is 4, 2 times 3 is 6, and so on. We remove combinations we've seen before. So because 1 times 2 is the same as 2 times 1, we remove 2 times 1 from this column here. So how would I calculate something like this using this functional programming approach? By the way, this program down here has nothing to do with this. It's a music program that I can present another time. Well, let me go through things step by step with you, and we can have a look. So maybe one of the first things we want to do is think about creating the whole table, maybe creating this part where we have 1 times 1 and 1 times 2 and 1 times 3. How can we do that? Let's have a bit of a look. Okay, so I'm just going to create a vector here, which contains a vector of integers from 1 to 9. That's the meaning of 9 ints. And I'll use my printing mode here. So you can see we have a vector, and inside is 2 other vectors counting from 1 to 9. Now we want to combine them together. What we want is for each number, we want to combine it with 1 and 2 and 3 and 4 and 5. So for example, in this column here, we've got 1s. But in the next column, we go 1, 2, 3, 4, 5, 6, 7, 8, 9. And there's actually quite an easy way to do that. It's a word called, or function, called distribute to the left. So if I activate that and I have to print it, as you can see, we have combined this whole vector, 1, 2, 3, 4, 5, 6, 7, 8, 9, with each number. Don't worry if it seems a little hard to follow at first. It is something you have to get used to. Now what we want to do is, well, we don't just want the 1 to appear only one time. We want it to be paired with each number inside this vector. So what we do is we use the word distribute to the right. what that means is you take the right element of a 2-element vector and you combine it with each element in the left vector. But because we want to do this for each vector inside of this list, we use the word all. So all is kind of like map in list. It replaces the idea of loops. We don't really have for loops in this functional programming style. We have functions and combining forms that have sort of an equivalent behavior, because really we're not thinking in terms of going through each individual element. It's more like we're operating on the entire vector at once. That's probably the best way to imagine it. So you don't have to think of all as going through each element. It could be that all is a word that parallelizes all of this computation. So we're parallelizing distribute to the right is another way of viewing it. So let's see how that looks. Now I might have to use a different printing word to get the format I want. So that works. Okay. That seems fine, doesn't it? 1 times 1, 1 times 2. Yeah, we've got the combinations here. Good. So now we can try turning this into a word. And I'm going to call it something like, oh, I'm not really sure. I'm just going to call it like LR for like left and right. It's something like multiplier and multiplicand, I think is the terminology. So I'll use MM. So MM now produces this. Look, notice I can create a definition just using colon like you normally would in Forth. So we got this, right? Now this is where the interesting part comes. According to Backus, we should be able to combine programs together. So we're now going to attempt to compute the result of each of these, the product. And we can actually use this previous table. All we need to do is we need to multiply each of these numbers together. So the word that I've defined to multiply 2-element vector is times 2. But we can't use it in its raw form. We actually have to apply it to all. In fact, we have to apply it to all twice. So we use this word here. So what this is basically doing is a nested loop. It's not just looping for each element, it's looping for each element inside each element. And if I compute that, oops, wrong way, you can see I get the results here. So product. And then we're going to get to what is my favorite part in a moment. Oh, let me reset because I might run out of memory. So we can generate this part and we can generate okay, let me see what went wrong there. Okay. Very interesting. Because when we did MM and we did times 2 and we did double all, okay, we couldn't do that. Right. Fine. I might have to restart my Forth environment here, or at least reload this again. Let's try that again. Okay, good. I'm always going to reset. And let's see if we can define product again. Okay, you can see the mistake I made because unfortunately with this version of Forth at least, you have to use a different version of tick. So now we should be able to do products. Okay, that's what I wanted to demonstrate. So now that we have both parts, which are programs individually, we should be able to combine them together. Now this is possible. And I might not explain every single step, but I will attempt to show you how this can be done. So take MM, or let's put reset first so we don't run out of memory. Take MM and prod. And then we want to put them both into a vector. And we use this word called transpose. Now, transpose is very good at combining things together. It's equivalent to transposing a matrix. So if I do something like 1, 2, 3, 4, 5, 6. If I do something like this and I transpose it, you can see that it goes from being sort of horizontal to vertical. But what it also does essentially is two lists get merged together. So you take the first elements, you put them together, you take the second elements, you put them together, and so on. So we're doing the same thing here with each of these tables. However, we need to do it for another layer, which looks more like this. So notice we're almost there. 1, 1 is 1, 1 times 2 is 2, 2 times 1 is 2, 2 times 2 is 4. Good. But it would be nice if we had each of these elements inside of this element to the left. So we also have a function for this, a program called append to the right. And just trust me, this is the word you need to iterate through and do it in the correct places. So now we get something looking more like our table. So this here is a multiplication table, isn't it? And we have created this using two programs that we wrote before and some additional functions and combining forms. So essentially we've taken two programs and combined them together, which is quite powerful. The final step I did is just to filter out any results I didn't want using my filter word. And there you go. That just removes any repetitive ones. This is very common in the world of array programming and functional programming because you're not thinking about each element you need. You're thinking about calculating everything at once. And then what you might do afterwards instead is say, okay, I calculated all the combinations, but I don't need all the combinations. So you get rid of some. It does sound quite wasteful, but either on the right hardware or with the right optimizations, it does actually work out. So we've gotten to the point now where we've produced this multiplication table. Great. So let's have a jump back. And now this is my final slide. Okay, so let's draw some conclusions now after this demo. So what did I learn from this project? Well, believe it or not, I've read this paper years ago. I think I read it even before I discovered Forth existed, but I did know Python. I have been trying for more than a year to implement this language in Python, and I've struggled. Maybe it's because I was trying to implement everything exactly right, but still, even then, I never produced something usable. But in Forth, knowing how to do this, it took me maybe 2 days, and I actually have something that's usable. Oops. It's also relatively compact. I mean, the engine itself is finished in, say, 16 lines, which would fit in a block. That fits in a 1/4 block. And then the rest of it are words that I want. So that's an advantage. Forth, I've realized, is actually really good for exploring new languages and ideas, and it's good for prototyping. I mean, who would have thought that you could do this kind of programming in Forth, functional programming, something that someone could argue wasn't an original goal of Forth. And then the next thing I realized is this, and this is maybe where this work crosses over a little bit with my work on the Forth CPU. Functional programming works really well for parallelism, because the way you have to think about your problem is not it's not word at a time, or sorry, I shouldn't use word at the time. It's not cell at a time computing. You know, you don't think I calculate this value, then I calculate the next. You take a whole vector and you say, which operation do I need to apply to the entire vector? You know, in this approach, you don't think of the one answer you need. You calculate all the combinations and then you select what you want from that. And I think that seems to be quite compatible with parallelism. One bullet point I've not put in here, which is going to be my final point, is John Backus mentioned something really interesting. I don't know if it's in this paper or in another one he did later, but it's the algebra of programs, right? As I say, the title of the paper, he mentions, let me see if he mentions it here, an algebra of programs. And it contains a concept such as being able to simplify programs or make them more efficient, just like you would with a quadratic equation. You know, you take it and you factorize it. This concept in programming, I think, is very powerful, this kind of symbolic manipulation. And it's something I'd really like to explore now that I have this engine working. So stay tuned, because what that would ideally mean is, rather than having these inefficient words that iterate constantly over a vector, you could design a program using these words, but then an intelligent compiler could go through and reorganize them according to the rules of algebraic programming to create a more efficient version that is actually better on resources. So yes, thank you for listening, and I'll open to any question.
That was awesome.
I definitely have comments, because one, Backus's paper, I actually think that he mentions Ken Iverson as being the guy who escapes the von Neumann bottleneck, and I think that his mention of Ken is why Ken got the Turing the next year and gave his talk on notation as a tool of thought. The other thing that's very interesting in Backus's talk is that he described a matrix or an array as being a list of lists. And one of the things that the APL community sort of got stuck in is the notion of having these multidimensional arrays, as opposed to just simply a list of lists of lists. And what you're pointing out about the fundamental structure of a cozy object, the header is first of all typed to say what it is, the first one, and the second is the count, and which is essentially, it's a generalization of counted strings, and going and moving the count into the object goes and allows the factoring out of the having to go and have the iteration, how many you're iterating over.
Exactly, which is what I noticed too. That's why I took that approach about putting the count in the vector and using sort of vectors instead of linked list. I figured that would be the easiest way to iterate. So I guess we thought we're on down the same path.
I hated linked lists from one of the very few things that I ever learned in about the one programming course that I took in like 1964. I disliked them as a structure then, and I just like simple lists. And you're absolutely right about I mean, this is the thing, and anybody who, well, I recommend K as being a simplification of traditional APL, and then Cozy having taken that all the way to the simplicity of Forth, and significantly simplified what even the somewhat screwy syntax of K and the very, very arcane syntax of traditional APL. But one of the really major factors is that when you start talking at functions, operators that operate on the entire object, on the entire list, then the notation becomes intrinsically parallel. And as you say, your implementation of that can be, particularly when it's in open Forth, can be matched to whatever array of hardware you have. And
Yes.
it really, the marriage, and again, the pointing out that the Forth is unique in its ability to make language word at a time and build up vocabularies to do things. And that's why, 30 years ago, when I first learned of the existence of Forth, having learned APL and been in APL, my immediate thought was, okay, you're going to build a vocabulary in Forth. What's the most valuable vocabulary to build? Well, it's APL. Go straight all the way, and have it open all the way from top to bottom. That's my rant.
Yeah, thank you for your thoughts on that. Yeah, and I realized that I think this is why I started to look a little bit into Cozy, because I saw some of these ideas are really fascinating. But the main lesson to me is just you can create look, if you're writing in Forth, you are writing at the level of beginners, basically, or sort of novices. But when you reach a certain level of Forth, when you become more advanced, of course, what I'm saying depends on application. If you're doing deeply embedded things, you're going to be writing just raw Forth, right? Especially if it's on a Forth processor. But like a more advanced topic, I think, is creating a language in Forth that solves your problem, and then writing in that language. And if you go back to the problem-oriented language paper by Chuck Moore, that's really the idea I think that is trying to bring across, but maybe has been lost by some people over the years. So yeah, thank you. Any other questions or thoughts?
Yeah. So one of the things I was thinking about with AI is you have a list of
no, thank you.
you have a list of like CFAs, which are, you think of them from an AI standpoint, their behaviors. And let's say you had a list of 10 of these things. And you can also combine the data in there, obviously, so CFA is a pointer to to a word, a function. And what if you had words that executed those, and then you had some sort of performance, which one gets you the result that you want, and then you move those CFAs around, and you can't do that with other languages. But it's a really powerful tool. I'm not quite sure how to use all that, but using these lists, this is really cool what you did.
It does, I think what it enables potentially is thinking about a problem almost as being a mathematical problem, or some algebraic problem. That's what I see as being the advantage. And I think that's, in some context, that higher level of thinking, I think, could be very powerful in the same way that when I was exploring Prolog, the idea of seeing a problem as a logical proof is also quite a powerful concept. And it's just probably one is good for one domain and the other is good for another domain. But the incredible thing is you don't have to switch to, you don't have to switch to Prolog itself. You don't have to switch to APL or some other, or Lisp or some other language. You can actually just use Forth. I mean, as I said, 16 lines, and I pretty much had the engine. Add a few more for words. That's maybe like 2 or 3 blocks of code. Yes, it's not a full application, but you may not need the full environment anyway. You might just need a few for. So I think if there's a point to take away from this, I would like emphasize that.
Blocks. Those were the days, the simple, halcyon days of youth. On that note, I'd like to move on